Hey everyone, thanks for joining us here today for this session. This is AWS Lambda Part 1, Optimizing Your Serverless Applications. My name is Chris Munz. I'm currently a Senior Manager and Principal Developer Advocate for Serverless Technologies at AWS. I've been in AWS now for just about 8.5 years across a number of different roles, but for the last 4 years focused on this space of serverless. And myself and my team are responsible for a lot of the content that you'll see, whether it be in blog posts, videos, events like this here, reInvent, summits, and all sorts of things. We'd love your feedback. I would love your feedback. So I will have my contact information at the end of this. But you could find me at my last name, Munz, at Amazon.com or at Chris Munz on Twitter. So why are we here today? So this space of serverless, this topic of serverless is obviously something that has a lot of attention from the industry today. We see companies of all shapes and sizes building things with serverless technologies. And it was originally just a little over 6 years ago at reInvent that we first announced kind of the core of the serverless space for us, which is AWS Lambda. Now, Lambda is a product that I'm sure most of you are familiar with. It is a compute product. And when we talk about Lambda, we talk about it being part of an overall architecture for building serverless applications. Now, what is a serverless application in this context? Well, if we take AWS Lambda, Lambda, again, as a compute service, is made up of what are called functions. Functions are the code that you write that represent your business logic, your business functions, what it is that you need to do for your application's needs. Today, we support a number of languages that are essentially considered first-tier languages. We also have the runtime API. And so with that, you could bring almost any language that you could think of to Lambda. And we've seen customers bring everything from PHP to Erlang to C and C++, all sorts of options there. Now, another component of serverless applications is the invocation source. This is essentially the front door to that business logic that you have. This is the code that you will be executing. And today, there are over 100 services at AWS that can invoke a Lambda function, as well as its API. So you can do almost anything with this, and we'll talk a little bit more about that here later. And then the other side of your Lambda function are the services that your code might need to interact with. This can be everything from databases to data stores to other APIs, all sorts of things that you would normally have an application interface with. Now, in today's session, we're going to be focusing primarily on the outside parts of the serverless application architecture. So we'll be talking about the event source, and we'll be talking about the services that you integrate with. Again, that's going to be kind of our main focus on this. Now, one of the challenges that we have this year in this format and in this setting is that we only have 30 minutes. So there's only so much that we can get through. And that's why I'm going to encourage you to really try to follow up and to check out the session that is SVS 405, which is the part 2 for this, which is done by Alex Casablani. And that is actually more of a focus on that space in the middle, which is your Lambda function. So there's a whole lot to cover here, even more than we could probably cover in one session. But do try to check out Alex's session in line with this. It's going to help you fill out that full picture. But let's dive into, again, these two aspects of your serverless application architecture and what some of the optimizations are that you can make. And I'll say that what I'm going to recommend today may not be applicable for every use case, but it is applicable for most. These are the generalized, I would say, best or better practices that we would recommend. And so I'd always encourage you to start with these and then invalidate that they're not right for your situation versus start without them and then figure out later on that you should have. Now, again, given the context of the timing today and everything that I want to cover, there's basically 6 main points that I want to cover across 2 different sections. The first, again, will be on that invoke or execution side. The second will be on the integrated services side. And so the points that you see here around using the right execution model, concurrency in you, handling errors and failures, that's again on the invoke side. And then on the integrated side, it's things such as Lambda storage options, database connectivity, and then managing secrets and configuration. So 6 different points across these 2 sides that we'll be covering here today. Again, a small snippet, but what I find to be some of the biggest, most important, impactful areas to spend time when it comes to optimization. So let's start off with the picking up the right execution model for your application. And this is one that I find that customers building serverless applications don't always understand all of the options that you have in front of you. I think there's a lot of people that are familiar with the concept of a serverless API, but the reality is that with Lambda, you can do much, much more. So setting some base kind of knowledge here, Lambda is an API-driven service itself. When you go to invoke a Lambda function, you are, at the end of the day, doing that through its services API, whether that's coming in through another service, whether that's coming in through code that you wrote directly against the API, all of those are going through this API endpoint that the service runs. And again, this is for both, which we're about to talk here in a moment, synchronous and asynchronous, as well as the polling or stream-based models. There is no other way to execute code in Lambda today. There is no port or socket that you can reach out to. There is no other sort of interface. It has to go through the API. And so everything that you do goes through that API. Now, what that API enables for you is 3 different models for how to be able to invoke Lambda. And I say these are 3 models that we see with the services that we've built here at AWS. It's hypothetical that you could use the API itself to do things slightly differently, but generally they're going to fall into these 3 buckets. The first is synchronous model. This is something that probably everyone listening to this is familiar with. This is the idea that you have a service somewhere, potentially say an API gateway like Amazon API gateway, that receives a request from a client. That request then goes and needs to talk to a backend. And so if you've used Lambda, then API Gateway will make the invoke or execution call to that function, which will then execute your business logic. And then ideally, if everything goes right, that Lambda function is going to return back to you a response. So it's going to give back some sort of information based on the call that you've made. So that is a synchronous model. Request goes out, response comes in. We also have an asynchronous model. And so the asynchronous model fits more with things like Amazon Simple Storage Service or S3, Amazon Simple Notification Service or SNS, where either say an object is placed into a bucket or deleted from a bucket or modified, or a message is put into a topic. And what happens from there is those services will invoke Lambda on your behalf. However, there's no path back up to the originating client, and there's no value in returning a response to that service. So this becomes a synchronous model, where after that work is done, you would have to have something in your application architecture that maybe reported on it or shared feedback or continued on that process. And again, that's the asynchronous model that we have. And then lastly, we have a stream or poll-based model. So the stream model that we have today is supported by DynamoDB streams and Kinesis data streams. We also support SQS, which is a queuing service. In that case, it works a little bit different than Kinesis and DynamoDB. Now, all of these models, typically what would happen is you would need to pull the messages or the data out of those services. And so what we do on the Lambda service side is run a poller on your behalf. And so that poller uses the same SDKs and API calls from those other services to consume the messages, to consume the data that comes out of them, and then takes that and invokes your Lambda functions on your behalf. And again, all of this is kind of hidden behind the scenes for you, but that's what ends up happening behind the scenes. So 3 different models, synchronous, asynchronous, and then the stream or poll-based model. And with this comes the flexibility of being able to build an application that could do, and an architecture that can cover almost any use case that you can think. Now, why bring this up? Why discuss this in a talk like this? What we find very often is that people are really focused on building synchronous-based architectures, and they're missing out on the benefits of the rest. Now, why is that a problem? Let's talk a little bit more about what synchronous means in this case. So you're probably familiar with the idea of just a request response model where you have a client, it makes a call to some sort of application backend, and then that application backend responds ideally with a success message. And for some reason, if it doesn't, then the client could go and say, okay, I actually need to retry this because there was a failure. And so you can pass that logic up to the client to say, something's gone boom, let me go back and retry that or handle that depending on what the situation is. Now this works great when you have a single service, but a lot of people today are building distributed services, distributed architectures, where you might have multiple handoffs or multiple calls that could happen. And so what typically happens then is service A calls service B, and then what you've done now is you haven't doubled the failure paths. You've in fact added many more times the potential failure paths. And so you have to start to think about, well, if the second service fails, does the first service handle it? Does it propagate the response back up to retry? What happens if the second service is successful, but the first service isn't able to retry? And so these types of architectures become very brittle. They become very problematic. They become very difficult to scale. And so we try wherever and whenever possible to encourage to not follow this model, but to instead build asynchronously. So again, for those of you who are maybe more new to this topic, what does this mean? So again, in a synchronous model, traditional client server, you have a request going to a backend and the backend replying. In the asynchronous model, typically what you would see is a request goes to the first service, then maybe it needs to go and make a call to that second service. But instead of waiting for the reply, it simply tells the client or the upstream service, hey, I've done this work. Can you now go and do what you need to do to request a response or an update from that? And so it changes the model in terms of how you have to think about that failure. For example, it may not impact directly up to the client. Perhaps that second service has some sort of state tracking that it's reporting on. Perhaps the client is smart enough to see that it has failed and retries directly. But what we find here is that this asynchronous model becomes really valuable for building applications, specifically the kind that we see people building with serverless technologies. So in general, if you don't need an immediate response, if you have a web or a mobile UI that can pull a backend or even take a push from, say, a WebSocket call, or just doesn't need an immediate response for whatever reason, you should really look at leveraging an asynchronous model. And again, specifically with Lambda, this is an incredibly easy thing to do. And in general, what we find is that many customers end up not needing any sort of synchronous interface in front of a Lambda function, and they can just directly use the SDK. Now, there are some gotchas to this. There are some places where we would offer up caution, but generally speaking, this is possible. When it comes to building asynchronously, I gave the examples before of things like SNS and S3. We actually have a number of different options that have a number of different benefits in them. Messaging services such as EventBridge, which allows you to put an event into effectively what we call a bus that would allow you to potentially send that event to multiple places. We also have Amazon data streams, Kinesis data streams, again, which allows you to stream data, collect it, and aggregate it and send it out. Now, across these four options, SNS, SQS, EventBridge, and Kinesis, there are a number of different factors that you have to think about. And again, that's far too much for us to be able to go into in today's talk. But what you'll find is that each of these options has certain different characteristics that can make it fit well for you. These are just, again, a couple of the ways that you can think about comparing these, whether we talk about durability or persistence, how they handle retries and failure logic, and then, of course, cost. For some of these, the cost may not align with what you're trying to do. And one of the big things that we try to push with serverless technologies is getting the value for what you've built. So again, really important to think about, do you always need synchronous? Do you always need APIs? Or can you do things asynchronously? Can you do things in a poll or stream-based model? And what might the benefits be of that model for you? So that's the first area where, again, encouraging asynchronous is one of the best practices that we have for building serverless applications. The next thing I want to talk about is concurrency. And I find that this is another area where people get fairly confused about how concurrency works with Lambda in particular, how event sources impact that, how the execution model impacts that. And so I find that I typically have to have a lot of conversation with customers about this. Now again, with Lambda, it's important to know that a single execution environment, or a single worker as it were, that is consuming from the Lambda service or from your event source can only process a single event invocation at a time. So for things like synchronous services or synchronous invocations from API Gateway, that's a single request. There's no batching, there's no parallelization inside of the function itself. With the asynchronous and stream-based models, Lambda can get a batch of messages. And so it could potentially process that single event made up of that batch of messages in parallel. Again, depending on how you've configured your function, depending on how you've written your code. But generally speaking, again, it's a single batch at a point in time. There is no ability for you to consume multiple batches. Now, concurrency in Lambda has another aspect to it in terms of how it scales, which is this concept of burst. So many of you are probably familiar with the overall concurrency limit that you have in a region. But another limit that plays into how Lambda scales is the burst rate. And so the burst rate is set per account per region. Depending on the region in question, there are different burst rates. So you can see here an example from the docs where it varies across a number of different regions. Now, this is a soft limit, but it's important to know that this does impact your ability to scale rapidly. And so sometimes you have to be cautious around that. So let's talk a little bit deeper about concurrency and how concurrency works for you. Let's take the example of an application that's going to receive multiple requests in a short time frame. What we see here is that I have a new application or a function that's being executed for the first time in a while. And so we see that it goes through the normal function lifecycle. And again, Alex covers this a lot more in his presentation on optimizing Lambda functions themselves directly. So our function gets an invoke or a new request. That causes a new worker environment to have to be spun up. So we see that this worker environment has a cold start. So the cold start's going to happen. It's going to do all the things that it needs to behind the scenes to get ready to execute my code. And then it's going to execute my application code, right? It's going to run what's inside of my function handler and do all of the things that it needs to do. Now, during this period of time, this environment is essentially blocked. It cannot be used for another request. No other data is coming into it. And so it is effectively kind of off to itself doing its own thing. So as I get more requests, because this environment is blocked, those requests will end up causing new request environments or new worker environments to be created. They will go through cold starts. They will then execute the code. And at some point, after that first environment has completed its execution, then it becomes free again. And so that environment is then open to take another request. And so we see here that request number 6 comes. Now at this point, I have a warmed environment. I no longer have to have a cold start. And so the execution just occurs. I don't have to worry about, again, waiting for that to happen. And similarly, this would happen for the rest of these environments. Over time, they complete their execution, new requests come in, those warmed environments are reused. And so effectively, I might, as you see here, only have a couple of these individual swim lanes where I have new worker environments that have spun up and go through cold starts, and then they will get reused over time. Now, what's important to note here is that the concurrency that you have at any point in time is dictated by the actual environments that are being, that have an active execution. So we see here how we start. Initially, I have just a single execution, then I go up to 3, then I actually go up to 5, and then I dip down to 4, and then I have actually 4 for a while before I peak at 6, and then I go down to 5. And so you can see here at this point in time which execution environments are active. However, you'll note that there aren't others being recreated if I have available warm. And similarly, I have to have them created if there's ongoing executions. So again, really important to understand there's effectively no multiple concurrency path inside of a single worker environment. So subsequent requests that overlap during an execution will create new environments. And then over time, as they free up, they will get reused. Why does this matter? Well, when it comes to thinking about how you would consume requests or consume events from your upstream service, the concurrency that's available to you and how that concurrency it basically is executed upon inside of your account becomes really important for understanding the scaling properties of Lambda. So just as an example here, if we look across various different execution models and the services that might be feeding them, we can see how based on things such as batching, based on how stream-based processing works, and based on how, for example, things like the messaging services with SNS might work, how you're able to process records in parallel. For some of these services, you're able to process much more in parallel, whereas for others, depending on the configuration, you could be limited by that. And so again, just an important context to understand around how concurrency, invocation, and execution models works. Great, so let's move on to talking about handling failures and retries. Now, when it comes to handling failures and retries, you might think that this is something that's important to know about for inside of your function. The reality is that there's a lot of opportunity for you to think about how this works from outside, specifically from the invocation side of your architecture and your application. So across the 3 models that we talked about before, the main point that I want you to walk away from is that you can control this across any of the models that we have here today. Now, a lot of this is due to some features that we announced just last year around retry controls, around bisecting batches and being able to retry aspects of that. We also now have a number of controls for synchronous and stream-based models for maximum age, for maximum number of retries. And so you can really get pretty fine-grained in terms of how you do failure handling inside of your architecture. And again, as you can see here, based on whether you are sync or async or, again, stream or pull-based, there are these different options that are available to you. Now, one thing you might want to look at if you are building asynchronous applications is a feature that we launched last year that I find that far too many customers still haven't really grasped a whole lot, which is Lambda destinations. And so what Lambda destinations allow you to do is a couple things. One is failure handling, which is super powerful. If your event fails or has an issue, you can then pass that message with a bunch of metadata into the destination and then do something else with it. As you see here, the destination could be a number of things. It could be another Lambda function. It could be an event bridge bus. It could be an Amazon SQS queue. And so you have different flexibility in terms of what you do with your application architecture. The other thing you can do is pass on a success. And so this allows you to do things such as chain Lambda functions together in a way that puts a async model essentially in between it. This can be incredibly powerful for building multi-step function-based workflows, and it gives you a whole lot of flexibility. Now, another option that you have is a service called, or a capability called dead letter queues. Dead letter queues today exist in Lambda, in SQS, and EventBridge. And what they allow you to do is to be able to capture those failed messages or failed events or failed requests into an SQS queue and replay them at some future point in time. Personally, I think that for Lambda, the event destinations is the better model. But depending on your needs, this can work for you as well. One other thing that I want to touch on here again about the invocation model aspect of things is around limiting the amount of events that you send to a Lambda function. And essentially what I find is that there are a lot of customers that will build logic into their function that acts as a filtering mechanism. So they'll take in all sorts of requests and then have that business logic execute in there, and it adds the invocation time, it adds to the complexity of their code. And that, in general, is not something that we want to encourage. So there's a number of ways that you can reduce the events that get to your function, whether it be from message filters that exist in a number of services, the rules that can come in from S3 events, being able to do path-based routing and API gateway. Again, there's a number of ways that you can do this. And what you want to remember is this key phrase that we have, which is you want to use functions to transform, not to transport. And essentially, filtering inside of a function is a model of a transport. You're kind of gatekeeping what gets through to your business logic or not. And so this becomes a really good place to think about how you can use these upstream services to limit what gets executed by your function. And in general, one quick way to think about it is in doing this, in utilizing these services, you're writing less code. If you're writing less code, then you're saving yourself from a lot of potential work in the future and things to maintain. And so again, when we talk about serverless, we have to talk about doing less. Less code is part of that. So now let's talk about the second half of this story here, the integrated services side of things. And again, this is the stuff that you will be talking to from your Lambda function. This is the other services that typically show up in an architecture. Now with Lambda, we have a capability called environment variables. So with environment variables, you're able to configure a key value pair that can be read from inside of your Lambda function. This is used to pass in everything from secrets to configuration information. These can be encrypted. There's a whole bunch of capabilities that happen with them. Now, one of the challenges is that they are specific to a single Lambda function at any point in time. So if you had, say, an API gateway, and you had a whole number of functions behind it, you would have to configure each of these as part of that. Now, another option that we do have is through a pair of sibling services, Systems Manager, Parameter Store, and then Secrets Manager. And the two of them work really closely together. They work very similarly. Secrets Manager has some added capabilities around key and credential rotation and integration with a number of AWS database services. But in general, these are things then, or services that can be configured to be accessed from multiple Lambda functions, from container-based applications, from EC2-based applications. And so you have a lot of options for how you would go about getting the various key value pair properties from these services into your application code. And so I find that the benefits of this centralized model are again, numerous. You also get security controls. You also get, again, consistency across your applications. And so when it comes to thinking about how to get that information in front of your functions, I find this to be one of the most powerful ways that you have. Let's talk briefly about databases. This is an area where, again, we could spend a whole chunk of time talking about, but I only have a little bit of time here in today's talk for it. What it comes down to is a couple of things. One, with RDS proxy, which I'll talk about here in a moment, it frees you up to being able to use relational databases in your serverless applications. Now, this was a common frustration for serverless app developers for quite some time, and was solved a little bit earlier this year via RDS proxy. The other is, if you can architect your applications with an HTTP-based database, then that actually is better for you. There are going to be numerous benefits. It's going to be easier for you to code for. It's going to be easier for your application, redundancy and availability typically. And so where you can do that is at times preferable. But again, any database that you can think of pretty much now works pretty well with Lambda without you having to go through a lot of hoops or doing a lot of different tricks. Again, when it comes to relational databases, if you are building with MySQL or RDS, you can now make use of RDS proxy. And so RDS proxy gives you, again, a number of benefits around being able to pool connections, around being able to have security managed by services like Security Manager and IAM really easily. Helps with things like failover between primary and secondaries inside of RDS. And so if you aren't using RDS proxy today and you are using Lambda with an RDS-based database, I would definitely encourage you to check it out. If you've been holding off because you didn't know about this solution, then I'd encourage you to check it out as well. So let's talk about storage real quickly here. With Lambda, built into the Lambda service, there are 3 different types of storage that exist just by default. The first is the memory configured for your function. So that can be anywhere from 120 megabytes to 3 gigabytes. The second is the temp space in the worker environment. So this can be up to 512 megabytes of local storage. And then the third, I should say, is your actual application artifact. So this is your deployment package, which can be up to 250 megabytes. Put that all together and it gives you a bunch of storage inside of your function. But we know that that's not enough for everyone. That's not enough for all workloads. So we also have access to is S3, which you've always had access to from your Lambda functions. And that can be used for storing temporary files, mezzanine files, outputs from things. But also, we recently launched over this past summer EFS support. So with EFS, you can mount a volume and get a ton of storage space that a Lambda function can execute upon or pull data in and out of. You can connect those volumes to containers or EC2 instances or something else, and be able to access the data on it as if it was just another server, as it were, that had mounted the volume. And so this can be really powerful if you do need extra storage space in a file system model and S3 doesn't work for you. But do check that out if you have an application that meets it. Now, connecting to all of these services, talking to databases, talking to things like parameter store, even talking to things like EFS and S3, one thing that you do want to watch out for is how large and how parallel your application can get. It is possible that you can consume all of the downstream resources of these services that your account is configured for based on limits and other potential restrictions that might exist. So one capability that we do have to help you control this is per function concurrency throttles. This allows you to limit the maximum concurrency of a function execution such that you could potentially protect these downstream resources. For me, I've always thought that it's a good safety net to protect things, to be able to control and watch out for, say, any sort of wild parallelization that I may not like or may not want my architecture to have to handle. And so it's a good thing to look at from the perspective of protecting those downstream services. Awesome. And then the last thing I'll talk about here again is when we talk about those downstream services, asynchronous, right? Think about how when you talk to other services, you can try to detach yourself from that synchronous model as much as possible. Great. So in closing here, again, really quick amount of time to get through all of this. So in just about 30 minutes, we've covered a whole number of topics. Some general guidance that we have here of things that you want to think about and try to avoid doing otherwise. And so, look at these points here, try to internalize them for the value that they provide for your architecture. Again, two main areas to think about, a number of different things. But again, there's so much more than there is to cover than we could fit into today's session. So I invite you to check out the link here that is in this QR code and in the short link code. That's going to take you to a resource page full of a ton of valuable links for you on this, more videos, blog posts, and other content like that. So check that out, please. And with that, my name is Chris Munns. I thank you for coming and joining me for this session here today. I hope that you found it valuable. Hope to see you in a future session. Feel free to reach out, always here to help, and enjoy the rest of this year's reInvent content. Thank you.